Okay, so we're going to see how to solve a couple of these today. I mean, one of them today. Let's solve the other. So this is the last talk. So let's recap those who were there last time. We showed that for a point-to-point channel with additive Gaussian noise, the optimal input distribution subject to a power constraint or covariance constraint is Gaussian. And how did we show? We used a characterization of Gaussian and used single-letterization arguments. That's what we did. And today we're going to solve a couple of those yellow problems, which is the Gaussian MIMO broadcast channels with private and common message. And as a part of this, you get something that was known before, broadcast channels with private messages in a very different way, the way that they wanted to know. It's a very straightforward way of getting this. We'll also, at the end, I just mentioned other application techniques. We'll not have time to do this. Hopefully, I'll finish quickly. So we'll go. So there's only 23 slides, but I'm going to do something on the board. It's not too long. So let me remind you what the characterization I used and proved was, is that if x and y are independent random variables, such that x plus y and x minus y are independent, then x and y must be Gaussian with the same covariance matrix. So this is the characterization we're going to use a couple of times today, or maybe once or twice. We'll see, but this is the thing I want you to remember. Okay, so this talk is mainly about what is known as a broadcast channel. Okay, I mentioned this last time, so let me remind you what it is. It's a setting where there's a single sender who is just shouting in the air, or who is just communicating in the electromagnetic waves, but it's kind of shouting in the air, and different people who may be far apart because of their local condition, they might hear two different noisy versions of it. And the conditional probability of, say, y given x is the conditional probability of y given x and z given x, that constitutes the channel. Okay? If the two channels hear the same thing, then it's not very interesting. It's a very simple problem. But the main thing is, if they hear different noisy versions, then can we make use of the fact that their characteristics are different to communicate more message? Okay, that's a question. So here there are three messages. A common message that both people want to decode. There's one message only for decoder 1, one message only for decoder 2. In practice, this could be some synchronization message or some timing message. This could be a personal message for both the receivers. And the goal is to compute the capacity region or set of achievable rates. This is defined by Tom Cover. Way on, this is still open. It's open for discrete membryless channels, and as we can see, for the vector Gaussian MIMO channels, which is very important in wireless, this is solved, and this is what we are going to see today. Okay, how to solve it for vector Gaussian channels. The best known achievable rate pair, rate triples, for this region is due to Martin, and she showed that for any set of new randomals u, v, w, such that they form a Markov chain, the set of all rate triples satisfying these inequalities is achievable. I want to give you some intuition about what these random variables are, u, v, and w. W is like the message that's common to both. Okay, so both of them decode w. That's what this condition. If you want to think of it, it's like that's what this condition says. So there's a channel from w to y, and if you transmit less than the smaller of these two, y and z can decode w. U is the private message to y, and v is the private message to z. That's kind of intuition for these random variables. That's the kind of intuition. It's not too off, but it's not exactly correct either. Okay, but it's a good picture to have. And as I said, she proposed this as a way of generalizing her strategy, which achieves the capacity for deterministic channels. And she didn't believe it's optimal. She didn't even think that's optimal. She just left it there. But it turned out that we don't know, even say this is 78, so it's like 37 years. We don't know whether optimal or not optimal, even till today. Okay, and this is one of the open problems, the gold, not the platinum one, the gold open problems in Gamal Kim. Okay, that's an open problem, just to know whether it's optimal or not. If it's optimal, of course, you solved a much bigger problem. But even if you can show it's not optimal, it's interesting. Okay. So this is the best achievable region for capacity. It means you can achieve these rates. So what is an outer bound? What can't you achieve? So this was, an outer bound was shown that the set of all rate triples satisfying these four inequalities, so there's a lot of minimums here, for any set of randomals u, v, w to x to y, z. If you take the unit of all, okay, this is the typo. if you take the union of all these triples, then you get a region which is outside the capacity. So what do we know? We know that there is one region. So this might be. So this is the unknown capacity. It's some curve. Let me ignore R0. I'm just drawing in R1, R2 plane. We don't know this region, but Martin showed that we can achieve some region which may be like this, and this outer bound shows that there's another region such that you cannot achieve any point here. So whatever coding scheme you choose. So this is an outer bound, so we call this U, V, W outer bound. And this is Martin's inner. And for a long, so UVW outer bound has some history, but the point is there were some other bounds which then reduce UVW outer bound like this. So it's kind of the best known for general broadcast channels. And for a lot of time, for 20 years, the way people showed capacity was, yesterday you can think of them as the channels for which these two collapse. And when I started looking at the problem, that this bound didn't exist, this bound is new to me, but the bound that existed was also had this property. Okay, so now we know more, and I'll tell you what we know. But if you want to play around, this is to me the simplest broadcast channel whose capacity is not known as of today. Okay? It's a very simple channel. X is broadcasting zeros or ones. Y gets a noisy version where every 0 is flipped equally to a 0, 1 to Y, but 1 is very clean to Y. Z, 0 is clean to Z, but 1 is noisy to Z. So that's it. So it's like a 2 Z channels in opposite way. So I call this a binary skew symmetric channel. And this is probably the simplest problem for which we have no idea of the capacity. We can evaluate things. So if you want to think around playing around with this problem, maybe this is a good starting point. It's a good channel. It's kind of very. They are both symmetric receivers. It's just if you flip zeros and ones, they are kind of symmetric, but we don't know what to do here. Or I think I know what to do here, but I can't prove optimality. So, and in particular, you cannot. The bounds will differ. The bounds I can show that they are different for this channel. So you cannot collapse these two bounds. So to prove the capacity, you have even some capacity. You have to come up with some improvement of either this outer bound or the inner bound. Okay, and if I were to pick, my guess is I can put almost 99 to 1 odds on the fact that this is tight. But that's all I'm going to say. I think the inner bound is tight, but I don't know how to prove the optimality. Okay, so for the vector Gaussian broadcast channel, which is the main topic today, you want to establish the capacity. And the idea is to show that these two bounds collapse. Okay? But if I say that these two bounds collapse, you would say that, okay, it should be simple. You just want to show that these two bounds collapse. The difficulty is really in the evaluation of these regions. Because you need our auxiliaries and we don't know what is the optimal auxiliaries. And I've spent a good part of it, not for this channel, but I've spent a good part in the last 7 years, which is my whole time in this field, trying to evaluate various regions and understand the boundary characterization. So I've spent quite a bit of time. Okay, it's not all for waste because I showed that in particular the bounds are different. I showed the outer bound is suboptimal, the other outer bound is suboptimal. I showed that this is suboptimal. I know that this is not true. So this is not capacity. I know. I also found new capacity regions, discovered new information inequalities which go beyond the setting.
Sorry, what do you mean by suboptimal?
Suboptimal means that I know a channel for which there is a gap. Okay? That this region is not this region. But I cannot write a general outer bound. So I have an argument for a particular class of channels for which I can get the capacity, but a general argument is still this. So that's the kind of state of the art of broadcast channels. And what I'm going to use is use single-letterization in the argument. So the way I'm going to argue for this, I'm going to look at this outer bound and show that Gaussian is the maximum. And that's the idea. Okay. So I'm going to do a lot of board work now. Okay. So I will start. Maybe Rafael can help me. But it's much easier to do on the board. And it's all the slides. So if you want to look at later, there are some argument slides because it's a set of things that it's easier to be done on the board, and we'll hopefully be done. So let's start with this. we're going to start with the private message. So what do we have? Let me start with what we have. We have Martin's inner bound. Huh?
Simulating your handwriting.
Too big or no?
No, it's amazingly beautiful.
No. it will go down in quality in no time. So, okay. So the inner bound is achieved. So what is the inner bound? So I'm going to set, in this case, I'm going to set in. Let me start with the easy case when I said there's no common message. Okay. It's not very easy. It's not any easier or harder, but it's easy. So there's no R0. So I'm only looking at the private message R1, R2. So in this case, Martin's inner bound is a union over auxiliaries U to E to W, so there's still a W, to X, to this is the channel, to YZ, R0, I mean there's no R0, so R1 less than I U W Y, R2 less than I V W Z, R1 plus R2 less than minimum of IWY and IWZ because both have to be decoded, and then plus IUY given W plus IVZ given W minus IUV given W. Okay, these terms I know them quite well, so that's why I can write them off the top. Okay, this is inner bound. Okay, that's the inner bound. What is the outer bound? So let me write UVW outer bound. R0 doesn't exist. So what is so R1 is less than or equal to minimum of IWY, IWZ plus IUY given W R2 is less than minimum of the same quantity IWY, IWZ plus IVZ given W, and R1 plus R2 is less than minimum of this the common kind of IWY, IWZ plus again another minimum of, so there are 4 terms, I mean, so I'm writing as minimum plus minimum IUY given W plus IXZ given UW, this sum or this sum, IVZ given W plus IXY given W. So that's the outer bound. So as a first exercise, I mean, the point of this exercise is to show how certain things work. I just want to get a feel of how arguments in this field work. So my first claim I'm going to show today, first claim I'm going to show is something very simple. In this setting, UVW outer bound is same, it doesn't exist, same as what I call the UV outer bound, which is R1 less than IUY, R2 less than IVZ. It's a union of, again, it's a union of all these variables. R1 plus R2 less than IUY plus IXZ given you minimum of, we can write minimum of this, or IVZ plus IXY given B. Okay, that's my first claim, that I don't need the W here. Okay, is that clear? So this is my first claim. Let's see. I mean, this is very, very simple, but I just want to get it. So this already reduces. When I put R0 equals 0, I only have UV, so it makes it my life a bit simpler. So why is this true? I claim that this direction is very simple. That this union is contained inside this union. You see, I can just put W to be something very trivial. Put W as a constant. And I put W as a constant, 0, 0, IUY, 0, 0, IVZ. So these two become exactly same. 0, IUY, it's exactly same. Okay. So therefore, when I take, so for every such pair, I can achieve that this region from this region. And this takes union over more random variables. So this region is at least as big as this. Clear? Is that clear? I mean, now how do you go the other way? The other way is kind of, okay, other way is not hard. Okay, maybe I should have put U prime, I mean, the union over, so it doesn't matter what the union is over. So here I just put U prime, for any UVW, just put U prime is equal to UW, and V prime is equal to VW. You see that this is bigger than this by chain rule, because IUWY becomes IUY given W plus IWY, so it's bigger than this. IVWZ is bigger than this, and you can verify that this is bigger than. I mean, if you combine this term with this part, you get this. If you combine this term with this part, you get this. So these two are. That's the way you show. Okay? It's not very hard. It's a good exercise. So this is my setting. So for so when you have any UVW, you set this pair to this bound. This region is at least as big as this. Therefore, this region. So therefore, these two regions are equal. So I don't need to work with this bound. I can work with this. I reduce my auxiliaries. This is a very useful thing because I don't need to worry about more auxiliaries.
So why is it that you don't start with this two square?
Oh, because I wrote the bound for the R0. With R0, you need this. Okay. So when you remove the R0 condition, you collapse. Okay. With the R0, you need. Yeah, so you start with this normally for private messages, but it doesn't happen here. It's not true that I can remove W. Okay? It's not easy, but there are examples like W, even though there's no common message, the W actually helps. Okay, so we're going to show that these, so in general we're going to show that, I mean, these two regions are same for, okay? So I don't need to, so this is my, in the middle I don't need, so that's the inner bound, that's the outer bound. Okay, again, so now I'm going to do again something. Now I'm going to specialize to Gaussian. Okay, before I do that, let me see. This is achievable for any UVW. Okay, that's what she showed. So in particular, I can set W to be trivial. So it's achievable for this. I can also, as I said, this is bigger, but I'm going to make myself so you can achieve this region, right? I can achieve this region. I just put W to be a constant element. There's nothing lost. So for the Gaussian, I'm going to show that these two are same. For this achievable as an outer bound, I'm going to show that these two are same for the Gaussian. Okay, for the Gaussian, so what is the Gaussian setting? Have y1, okay, y is equal to a times x plus some Gaussian noise, and we call it g1, and z is equal to some b times x plus b2. That's channel model. Okay, this is channel model. So I have some matrix type, some vector or input vector. So this is channel model. And Gaussian, so channel model, and g1 and g2 are g1 and g2 are 0 and okay, that's a setting. And I want to show that for this model, when I evaluate this region and this region, they collapse. That's the proof idea. That's what I want to show. So what I'm going to do is I'm going to evaluate this. I'm going to evaluate this and show that I can. So this is an outer bound, and I can show that every boundary point here is contained inside that. It's enough. So how do I show this? So again, I'm going to use supporting hyperplanes. I'm going to evaluate. So for every lambda bigger than or say bigger than 1, I'm going to evaluate R1 plus lambda R2 in the outer bound. So I want to maximize R1 comma R2 element of the outer bound. Let me call it outer bound. I want to evaluate this rate pair, and I claim that this is at least is at most maximum overall input distributions P U so in this case which is lambda equals 1, so PVX lambda IVZ plus IXY given. Why is this immediate? Because so R1 plus R2 we know from the outer bound is less than IVZ plus IXY given me. That's a condition there, right? And we know that R2 is less than IVZ. That's another condition. V prime. I'm ignoring the primes here. So if I do lambda minus 1 times this, it's positive. Lambda minus 1 times this. If I add these two, I get exactly this. Okay. So I'm going to show that this is achieved by Gauss. So that's the idea. So this comes from just the outer bound. I'm going to evaluate this, and I'm going to show this achieved. Okay, that's the idea. Okay, let's see. It's very simple. That's why I'm hoping to do it on the board, because you will see why it's simple. Okay, I want to evaluate this. Now I don't need the outer bound any longer. Evaluate. I'm going to remove this. So okay, let's see why. So as I told you before, I'm not going to do optimization. This was an outer bound for some reason. We started from a code book, and we got the outer bound. Let's see how we got the outer bound. That's single-letterization. And I'm going to show Gaussian just from the single-letterization. That's the purpose of the whole talk, right? So how did we get the outer bound? So we know. So what are the tools that we had last time? We had Fano's inequality. So let me remind you what that is. Fano's inequality, which was if I have two random variables m and m hat, say they are both taking values in say 0, 1 up to 2 to the power nr minus 1, then the condition and we know that probability of m not equal to m hat, the decoding error is small, then the conditional entropy of m given m hat is also going to be small, in the sense that if I take 1 over n of this, it's going to be less than 1 over n plus epsilon times r. Okay, that's Fano's inequality. And the other tool we use is that if x to y to z is Markov, then the mutual information IXY is bigger than IX. This is called data processing. These are the only two tools, and these are only tools we'll use today too. Okay, so these were two things. Use data processing, and that's all. I mean, that's the whole idea, and we are going to push. Okay, how do we prove this? So we know that y2, the receiver Zn can decode m2, right? There's an m2 hat can decode m2. So what do we get from Fano? We get nr2. Message is uniform, so this is h of m2. But that's also equal to, by chain rule, it's h of m2 given m2 hat plus im2 m2 hat. Now this is small because probability error is small, so this is, so if I do, so this is less than, if I multiply by n, so it's 1 less than or equal to 1 plus nr2 epsilon plus, now m2 hat is a function of yn, so I can write im2 for the zn, im2 zn. So that's the, so I use Fano here, data processing. That's the way I get this. Okay. What is NR1? NR1 is entropy of the message, first message, but the messages are independent, therefore it's also the entropy of the first message conditional on second message, because the there's the independence of messages. So that's equal to h of m1 given m2 yn plus I m1 yn given m2 as chain rule. This is small, so this by Fano this must be less than or equal to, because from y1 and I can decode m1, so but by Fano this is small, so it's 1 plus n epsilon r1 plus, I'm using data processing, so I have m1 to m2 to xn to whatever comes out. So the data processing is less than I xn yn given m2. Okay, so this is elementary, so we get immediately that nr1 plus r2, okay, let me ignore, or r1 plus r2 is less than or equal to, I'm dividing by n, so this becomes small, and ignore the epsilon terms, so I get is less than 1 over n times I xn yn given m2 plus I m2zn. Okay, that's an outer bound for any code. I'm ignoring epsilon terms, which is going to 0. So look at this term, this expression, and this expression. If I look at the n letter, like if I look at blocks, I can put v equal to m2. Correct? I can put v equal to m2. It's exactly the same thing. V is n, and xn yn given v. Okay. So this is, and so in particular, this is going to be less than the maximum. So this is less than or equal to 1 over n max over all p of v and xn. So I said v to xn to this is Markov I xn by n given v plus ivz. That's how. So this is where we start. The whole outer bound chart from Fano. So the only tools we use is Fano and data processing. There's nothing else we use. And we get this expression. And how do we get an outer bound? The outer bound is got by showing that this maximum 1 over n is exactly same as this maximum. Okay. If we show that, then this is an outer bound, because I can always obtain this by just saying, if I take independent copies of this, I'll get this. Okay. So this is, in general, this term is at least as big as this. So the whole difficulty is showing that these two are equal. That's what I call single-letterization. And the way to do single-letterization becomes not very hard, but it requires practice. I mean, so it requires a little bit of practice to see how these two are equal. So we'll show. So let me start. So, and I said I don't want to do from n to 1. I just need to do from 1 to 2, because that's enough. Because 1 to 2 is 2, 4, 6. I mean 2, 4, 8, and so on. So I'm done. So I'm going to do. So how am I going to do the single-letterization? So I'm going to show, this is the claim. I'm going to show that for lambda bigger than 1. Why am I looking at lambda bigger than 1? Because that's, in general, that's enough. Because if I do lambda bigger than 1, if lambda less than 1, I just flip it over and get the other one. So this gives you all the hyperplanes I need. Lambda bigger than 1, I'm going to show that 1 over 2, the maximum over PV x1, x2 is joint log of lambda IV z1, z2 plus I x1, x2 y1, y2 given v. This is equal to the maximum. So in general, I just have to show this because other direction is trivial. PV x lambda IV x. Right? This direction is trivial because this is smaller and this is trivial because I take the maximizer here, I take 2 independent copies, I get at least that. So that's easy. So this is the harder part. We always show this direction. So let's show that direction. So this is what, and what I claim is that this proof, if you mimic, it's essentially comes from this argument. So if you look at the papers which get this outer bound, okay, this was there in an old paper of mine about, but it's also in Abbas. I mean, this, if you want to see this argument, there are at least 3 references for this. This Gamal 78 essentially has this idea. Gamal 78 at Abbas. There is also Kerner Martin, this Kerner Martin 78. They were roughly same time. Okay, there's also UV outer bound also is there in a paper by me and Abbas in 06. Me and Gamal. So, okay, this single-letterization, see. But what I'm going to show you is how single-letterization. So you don't need to see this. I can show you. I'm essentially showing a proof from 2 to 1, and that's all you need. Okay, so that's some history. Okay, how do I show from 2 to 1? Okay, so let's go from 2 to 1. Okay. So let me call D. Oh, no, let me call. So observe that lambda I V. So okay, we have, what do we have? We have U. There's only V here. Okay. V to x1. I'm going to write the Markov chains here. X2. Not necessary, but this is y1 z1. Okay, I'm going to draw this picture. What does it mean? It means that I first generate V. This is a way of drawing conditional distributions. I generate V, I generate x1 from V, then jointly distribute x2. But the channel outputs y1 and z1 only depend on x1. They input y2 and z2 only depend on x2. It's this picture sometimes there's a name for this. Forget the name for this. There's a name for. It comes in Markov random fields. Okay, and Bayesian networks. And this picture is very useful because you can just read off Markov chains. There's also a rule for reading of Markov chains. What is it called? Do you know what the rules for reading of Markov chains are? You look at the paths. There's a rule for reading of Markov chains. Okay. Anyway, so what is IV Z1 Z2? So plus IX1 X2 Y1 Y2 given V. So I'm going to show how to do this. This becomes equal to. I'm going to use chain rule. Okay. You can stop me if you don't follow chain rule because I'm not. It's mostly very. If you work with this, the algebra is very simple. Plus lambda I V Z2 given Z1. I'm just breaking up this term. Now I'm breaking up this, but I'm going to use the Markov chain that y1 depends only on x1. So it's I. Okay. Let me do it first easily. Plus I x1 x2 y2 given v y1. I'm going to, okay. Sorry. I'm going to break it up this way. Z2 and Z1 given Z2. Break it up this way. Now observe that y1 just depends on x1, so x2 sits behind x1, so I can remove this, and y2 depends on x2, so I can remove this. So this is the first thing we do. Now here is something. So this I can write this as lambda. The first term. Look at the first term. What I'm doing. Write this as v y1 z2. I'm going to write this minus lambda I y1 z2 given v. This is just chain rule. So I'm going to add and subtract this term that gives me this. Plus I still have this plus lambda I v z1 given z2 plus, now I'm going to do something here. So I'm going to write this as I x1. Okay, do I want to do it in one step or two steps? Okay, let me do it in one step. vz2 plus I z2y1 given v. Okay. I claim that this is equal to sum of these two. Why? Because by chain rule, if I add these two, z2 comes up here, but y1 only depends on x1, so it just becomes this. That's so there is a bit fast, but you can just work this. It's there in the note. I mean, hardly there in the notes. I mean, the slide, so you can look at this. Plus I x2, or the term I'm missing, x2 y2 given vy. And now I can put this up. Okay. So the last step is lambda I. Observe that these two terms are exactly same. Okay. So it's I vy1 z2 plus, I'm going to add plus I x2 y2 given v z1 plus, so lambda. So now I'm going to do one more thing. I'm going to take it up here. Again, lambda I v z2 z1. So I have to subtract out lambda I z1 z2 because I took z2 up, plus I x1 y1 given v. Where is it? I x1 y1 given v z2. And when I combine this term with this, I get minus lambda minus 1 minus lambda is equal to 2 I y1 z2 given v. That's so. Now you look at this for any v. Look at this term v y1.
That's the
Oh, v y1. So the same term, and this is the same term as this. This is the same term as this. So clearly, this is for a single channel. So this value must be less than the maximum value here. This value must be less than the maximum value. The channel is same. So this must be less than or equal to, and these terms are positive because lambda is bigger than 1, and this is positive, so this must be less than twice whatever I want. Nice. Okay, that's the entire proof of single-letterization. Okay. Now we are almost done. I mean, this is known from like 70s. Okay, so why are we done? We are almost done because now we know how do we do with Gaussians. If it's Gaussian, I use the same trick. What trick do I use? I now put x plus. That's a trick I told you last time. X plus is equal to x1 plus x2. I take two things, x1 plus x2. I take the maximizer. I do this. So I start with the maximizer. I do this x minus to be x1 minus x2 by root 2 and so on for all the three terms. The channel is same because g1 plus g2. The channel is same. So I start with the twice the maximum. So I start with, so now here you get v1, v2. So I start with twice the maximum. So I get v1, v2. So I get twice m. So I'm going to modify this. So I get v1, v2 and so on. But this must be equal to this, and here. If it's true, this is at most m. This is at most m. So this must be 0, and this must be 0. Correct? Because that's twice m, because this is at most m, this is at most m, so twice m. So now so what do we have? And we do this with plus and minus. We do the rotation, so we do with plus and minus. So what do we get? Following this, exactly mimicking this procedure, because this whole procedure is valid. So we get the following. So we get that, at the end what do we get? We get I y plus, say that's my first term, z minus given v1, v2 is 0. And I also get that I z plus z minus, it's not required, but z plus z minus is 0. Now clearly so what is z1 and z2 are chosen to be independent because they come from two independent distributions. Z plus Z minus. So this is saying that Z1 plus Z2 is independent of Z1 minus Z. So therefore this implies, in fact it implies x1 x2 are Gaussian because the inputs in standard are Gaussians, independent Gaussians, that we know. But this gives me something more powerful. What does it give me? It gives me that for every little v1 and little v2, the conditional law of y1, yv1 and conditional or yv1 plus y1 v1 plus plus y2 v2. So this must be independent, which essentially gives me that x v1. When this independent gives me for every v1 v2, I have that x v1 and x v2. The inputs to the channels must be independent. X plus v1, x minus v2 are independent, and they have xv is the law of x condition v equal to v. Are independent Gaussians. Are independent, therefore we know that they are Gaussian because this x1 plus x2 by root 2, x1 minus x2 by root 2 with the same covariance. Okay? So what do we know? We know that therefore this is maximized by some Gaussian with some covariance. So in fact it's P. So it's immediate that this is maximized by some xv. So xv must be Gaussian. Say some mean can be different. I don't know about what the mean is, but the covariance is some k prime because I have a covariance constraint, and that satisfies the covariance constraint. So that's all I know. I know that the maximizer has a conditional law of this and a total law which is x. So you can know that you can easily show that x must be 0 k. So that's the whole. That's the proof of Gaussian optimizers for this, because I just did the plus minus. You get this. You get this as 0. So you have this. So that we have done. Okay? So you see, I didn't do anything. I just had this argument from 70s. I used this trick, and I could conclude from these terms immediately that they must be 0, and as a consequence they must be independent and they are Gaussian. No, I have to do no work, essentially no work once I know this characterization. That's the whole point of today's, the two talk. That when you have a single-letterization argument, you take the difference terms. People used to throw these terms away. You pay attention to these terms when, and these are useful in general, right? This is a trick that okay, maybe this is not the right transformation, but you can use this trick in other places to get properties of the optimizers. Okay, and that's what we are interested in, because we want to interest in the boundary. So don't look. So there is some information here which we threw away, but if you look at the information, what it gives us is the Gaussian optimizers.
Where have you ever used the lambda?
Oh, lambda because 1. Oh, so this is lambda minus 1. Because minus lambda plus 1. So this must be lambda minus 1. Otherwise you use some other. I mean, if it's other, you take the other.
Otherwise you will know that this is strict.
Yes. Exactly. And I need lambda strictly greater than 1. If lambda equal to 1, I use by continuity of this. So that's essentially. So you see, that's the point I want. It's a very simple argument. This is known from long time ago. You just put this, you're done. And I'll tell you what. And the rest part is actually 2 lines. So then you're done. So we can go back to the slide. So this is the calculation I want to show you that this is all. I mean, the proof is almost done. And my talk is almost nearing done. So don't worry about it. Not okay, at least 20 minutes, but it's nothing more. So all of this is there in the slides, but not with all the steps. So this is what I showed you for binary inequality, all of this, and optimality. You do this trick, you get this. Well, at least this part is explained better than what I did now. I just rushed over this, but there. Okay. Actually, I want to do one more thing, but I'll keep this and show. So this, what we showed is that for some random variable k star, and x distributed like this is on the boundary of, at least on the boundary, outside the boundary of the capacity, or at least on the boundary of the capacity. Okay, and the question now is the following. We showed the bound this for some rate pair we know the boundary. Can I achieve this? That's the question. Right? Can I always achieve this rate pair for Ek star? Okay. That means, can I construct a randomly u prime that may not be the same as u, which could be jointly distributed with v such that I want to make sure that this difference is ixy given v. Why do I want this? Because, okay, now you can look at the board. It's not a big calculation. No, there's no calculation. So the question I'm asking is the following. Oh, I know the outer bound is lambda IVZ plus, so lambda R2 plus R1 I xy given v, and I'm asking whether there is a u prime such that I u prime y minus I u prime v is equal to ixy given v. Why is this? If this exists, I claim I'm done. Why? Because I can always achieve R1 equal to IU prime y minus IU prime v and R2 equal to IVZ. I can always achieve this pair because this triple satisfies, with this u prime, it just satisfies this inequalities. If u prime y minus u prime v is less than this, this is exactly this and this is IVZ. Okay, if I could do this, then I could get this rate pair because it's exactly what I have. So the question is, can I obtain this? Okay. So if I can do this, then I was done. Okay. And in general, okay, maybe I'll show it to you. It's a very simple exercise to see that this is bigger than this. This comes out of bounds. How do we show this? So IU prime v u prime y minus IU prime v is less than or equal to IU prime y comma v. I can put a v here minus IU prime v. Obvious because we should make it only increases if I put more things. But this is equal. I can use chain rule to say that it's equal to IU prime y given v, and by data processing this is less than or equal to ixy given v. So it's clear that much also from the outer bound inner bound, but it's clear that the inner bound is less than the outer bound. But you can also, it's clear that this term is at most this. So my question is really whether I can achieve when they're Gauss. Okay, now whether I can achieve in general. Now I know that the only thing I know in excess is that they are Gaussian distributed. Does there exist a u prime such that when I substitute, such that you can get this exactly? U is u plus 1. Well, this is a question. Thankfully, it was answered by Max in early 80s. So this is exactly dirty paper code. This is exactly, this is nothing. So this is really, why? Because what he showed is, so in his state, V was a state, okay, V was a state, and so the sender knows the state. So here the sender is the same person, so he knows the state. So in his problem, he had to optimize IUY minus IUS, that's the Gelfand-Minsker thing, when S was a state variable, and he needed to make sure that you could achieve as if both people knew the state. That's exactly dirty paper coding. So once you realize that now you're back to dirty paper Gaussian dirty paper coding, this is from 81 or 82, very, very early on he knew this result. In fact, this is his choice. Okay, if you apply the vectors, this is exactly his choice. So if you apply u prime to be x u plus av, so what is the intuition was that you don't find the state vector, you use the state vector to reach a code word which are very far apart. That's the, am I right? Yes, so so the intuition is that you don't find the state, you don't find the noise, you actually join with the noise to get to code words that are far apart. So this is kind of the V star is kind of the interfering thing. So you do u plus a V star. This is the independent of this. So you join with u plus V star to get a code word.
It's like
and
judo.
Yeah.
You use the opponents.
So you use the opponent's strength to push him over. Right? So that's exactly what it is. So but this is known from the early 80s. So if you do this particular choice, you get this. It's just an exercise to verify. Okay? It's a very simple exercise. You can verify this. That's we are done. That is the proof of Mimo-Gaussian capacitance, complete proof of vector capacitance. Okay. To compare this technique to the original technique, okay, what did we show? We showed basically the Optimality of Gaussian it was showed the output is achievable by using a dirty paper. This is the whole thing what I showed now. How did people show first time 7 years or 8 years ago? It was really a 30-page paper in optimization. Okay, this one the best IT paper award. It was really, they had to use channel enhancement, they had to MAC BC duality, a whole bunch. It started from 2001, 3 different people with some rate. It was 2 different. I'm not belittling anything. It's a very nice paper. There are some very nice ideas, but it was really a 2D force. Okay. Now you saw the whole proof in half an hour, entirely. Nothing. I mean, there's nothing I left out. Okay, maybe except I still maximize it, but that's very simple. So this idea of just going to plus and minus, and I mean, it's a very simple idea, but it seems very powerful. And in fact, and the point is that they could not extend to private and common messages. They tried, other people tried, a lot of people tried, and I was teaching this their result in the class, and that's when I said there should be a simple way, because what they were showing was that 4 different regions collapsed, and there should be a much simpler way than that. So I was playing around with this, and then we observed this, and once you observe this, we're done. I mean, the whole thing. Okay? So we needed one other insight for the common message. Okay, but it was the min-max theorem that we already had for discrete channels. I'll tell you what this, because this was a very useful tool. Other problem. That's why I'm going to spend a few minutes on this min-max theorem. As Rudy said, Rudy was looking at all fixed point. I mean, he had fixed point theorems, and he needed fixed. So a lot of min-max theorems in math. Okay, the one that we wanted was established by somebody called. Before I go there, let me say. So this is outline is what. This is a UVW bound, because you have now R0, R1, R2. And I'm looking, okay, here's a, let me see who's awake or who's even partially listening to what I'm saying. I claim that I just need to look at these hyperplanes. Lambda 0, R0, lambda 1, R1, lambda 1 plus lambda 2, R2, where lambda 0 is bigger than lambda 1 plus lambda 2. You don't need to follow anything what I said before to understand why you need to follow this. Why is it enough to look at this plane? If it was less than or equal to, this is a common message, I could have put R0 into either R1 or R2, right? And it will increase it. Right? If this weight was smaller than either of the 2 weights, I could, I mean, if both can decode it, clearly either person can decode it. So if this is not true, then it's just private messages. So this is supporting hyperplane, so you don't need to worry about this. Okay? This is it's not a big. So here's the min-max claim. Okay? This is really a min-max claim. I claim that if I take the maximum of all joint distributions of this expression, the same as I first take the maximum. Here the C, there's the minimum over Ix, Iwy, Iwc, which is like I can write this alpha Iwy, 1 minus alpha Iwc, I take minimum. So I'm interchanging the order of minimum and maximum. Okay? And I claim that I can do this. Okay, why am I interested? Because when you do calculus or anything, this is much better behaved than max or min expression. Max or min is, you could have one function be the minimum, the other function be minimum, you lose all kinds of nice properties. Okay? If you could linearize it, it makes your life a whole lot simpler. Okay? So, but you need to justify this, because usually this is larger than this. Okay? So how do we justify this? There are a lot of min-max theorems. The min-max theorem what we need is by Cherkassel. So this is min-max theorem is the following. I'm putting it here because, I mean, okay, there are 2 reasons I'm putting it here. First of all, I mean, you need to know what you want, and I'll show you what we do. So what did he say? X be a compact connected space. Okay. What is compactness? Compactness means, you know what the word compact in English is, but in math it means that in math it essentially means that, what is it? How do I want to say it? Okay, if you look at topology book, the definition of compactness, every open cover is a finite subcover. Okay, that is absolutely meaningless to anybody but mathematicians. What it means is that if you want to, actually limit points exist in the set. You don't need to go out. I mean, if you take an open cover, you can just throw it. You can just need a finite collection. Or if you take intersection of closed non-empty sets, they will have non-empty intersection. It's a very nice thing. If you take a sequence, the limit will be in the set. Kind of. That's a kind of idea. If you take a sequence of points, then the subsequent conversions. Okay, that's only true in some spaces, but for most places you will see that's true. It's a very nice property to have. It's a compact set. So for most cases when you see you have a closed subset of the Euclidean space, it's compact. What is connected? Connected just means that if I have 2 points, then I can draw a path between the 2 points so that all points in the path belong to the set. That's connectedness. Okay? And what he says that if I have two, for every y1, y2, there must be a point y0 such that this inequality holds. And then the other condition he wants is that if you look at any y and alpha, and look at the sub-level sets, I mean these are the functions of x which are lines, this must be very close connected. Then you can explain. This looks very complicated. What does it have to do with what information theory? But it's a good thing to be able to read math. Right? If you read math, then you can apply it. If you don't know what these terms mean, that's one thing I want to say. I just put a slide to tell you that even though you may not use topology in your daily life, you must be able to understand what the statement says. Otherwise, you cannot use it. You don't know what it means. Okay. Anyway, so what we did is, okay, we want to use a theorem that most information theorists can use. So we proved a corollary in an earlier paper. We showed that, okay, if you have some set of constraints, then you can always, essentially you can always interchange the min and the supremum. So you have some okay, how do you read this? This some rate constraint on a set of variables. It doesn't matter what the variables are. You want to take some convex combination of these random variables, that's what a simplex does. So if you want to take convex combination of rate constraints, you can always interchange this as long as this set is a convex set. Okay, that's our condition. I mean, we show that this is a corollary. You can get this from the old result. But this, for most users, you only need this result. And the reason why we get convexity is also very general. Convexity comes from a time sharing argument. This is kind of, you can do one thing from fraction, one thing from different fraction. Okay? It's a very general. So most people, you only need to use this corollary. There's something, okay, the corollary is not very immediate, but it's not very hard either. Okay? So you can always transform a max min to a min max, which is very useful. And now you're done. Okay, now the claim is that the maximizer of this for any such pair is a 10-way Gaussian distribution. I'm not going to show the proof. It's exactly the same as UVW outer bound. Okay, the same, exactly same mimic argument. You can mimic the argument, you get exactly. There's nothing new here. Okay, that's essentially there's no. So once you have this min max m, you're done. Okay, so thus I'm almost done in the sense that we showed that to show the outer bound is achievable, it's the exact same thing. The outer bound is the same. So you show that. So you show that dirty paper coding choice works. And thus we saw this problem which is open. Okay? So the takeaway message is that maybe you need to reprove existing results in a different way, and then you get to take up, and you get to do more. Okay, that's the main thing. Okay, so this technique was developed 2012 January. It was published only last year. So it was 2012 January, and it's already been used. So this guy, before even I published, I put up an archive. 3 months later, he already published 3 papers using this trick to other things. Okay, so he's good. So but he could use this immediately because it's immediately clear what he could do with it. And you can also get a simpler proof of secrecy capacity. It's there in appendix as a remark that you get the single letter, you get it for free. This is another. This is probability theory. You can also get in probability theory. There's a very nice result called hypercontraction. It's a very nice concept, and it's a very celebrated result from the early 70s. It took physicists about 14 years and managed to prove it. But now you need a very, very simple proof using this technique. Okay? It requires a couple of things, but it's not very. Then this Tom Coutard, who's a young faculty member in Berkeley, he had posted a conjecture on a 23 blog like a year, 2 years ago. Then he saw this and he could immediately use it to establish his whatever his conjecture. So this has used beyond the broadcast time. So it has used either recovering results or getting new results. It's kind of a very useful tool. Okay, that's all. Done.